now that we've talked about ideal sampling, let's turn our attention to practical sampling, where here in a practical sampling case I'm going to generate a sampled signal by multiplying the original continuous time signal, not by an impulse train, but now by a pulse train. And so again, if my x of t may look like this, some arbitrary shape. But now if I multiply this by a train of pulses, all with height 1, and they're all spaced t apart, from leading edge to leading edge, or trailing edge to trailing edge. So this is what I'm calling pt of t. This goes on in both directions. What this product would look like would be, again, it's a little easier for me to sketch in first x of t, or at least the amplitudes for x of t, and then when I take the product of these two waveforms, would look like this. You get a pulse train, but now the amplitudes of these pulses are going to be affected by the x of t. Okay. The pulse tops will actually have the same shape as x of t during the time interval of the pulse. So this is what I'm calling now our practically sampled version of x of t. Well, we haven't talked about methods for doing this. You can imagine perhaps maybe a switch opening and closing to pass x of t on through a circuit or system during a particular time interval. We may talk more about this later. We can express, just like similar to what we did for coming up with the Fourier transform of the ideally sampled version, we can express any one of these pulses as a p of t convolved with our infinite pulse train. So where p of t looks like this is just a single pulse of, we'll say the width here is delta t and height 1, but when we convolve with our infinite pulse train, our infinite impulse train, it gives us an infinite pulse train. So again, starting with this expression for x over bar of t, it's now x of t multiplied by our pulse train, and then so in the frequency domain we'll have 1 over 2 pi x of omega convolved with the Fourier transform of our pulse train. Right, that is 1 over 2 pi x of omega, and convolved with, now our pulse train is p of t convolved with our impulse train. So in the frequency domain, that's going to become p of omega, the Fourier transform of this function, multiplied by the Fourier transform of our impulse train. And that's 2 pi over t, sum from k equal minus infinity to infinity, delta omega minus k omega s. I can simplify this a bit and write it as x bar of omega is equal to 1 over t x of omega, then convolved with that sum k equal minus infinity to infinity. When I multiply my p of omega times the shifted impulses, just going to end up evaluating P of omega at the impulse location. So P of k omega s, so these are just constants for the different values of k, times delta omega minus k omega s. And I can carry out this convolution as well, and over t sum from k equal minus infinity to infinity, and I'll have pk omega s times now x of, when I convolve x of omega with the impulse, I just get the shifted version of x of omega. And what this will look like, again, this is a sum of shifted versions of x of omega. Previously, we had a 1 here, where now we have these different constants for corresponding to the different values of k. So again, as long as I meet that the sampling at a rate greater than the Nyquist rate, what I'll have for x bar of omega is again these spectra plus b minus b that now repeat at omega s and 2 omega s, but now the heights of these will actually be different. Previously, the replicas all had the same height. Now the height's actually going to be determined by what's the value of the Fourier transform of P of t at omega s, for example, and then at 2 omega s and 3 omega s, and so these replicas will all have different heights, unlike with the ideally sampled case where all of the heights of all the replicas were identical. So although not this practically sampled spectrum is not the same as the ideally sampled spectrum, you can see that if I low pass filter x over bar of omega again, then what I'm doing here in the frequency domain, of course, is taking the product of those, and then the output of running x over bar of omega through this low pass filter will give me this result, which is, again, at this point, maybe have a slightly different amplitude, but it has the same shape as the spectrum of my original x of omega. And so I have recovered then the original signal from the practically sampled version of the signal in this particular case.